What's up, everybody? Welcome to lesson 12.3 for geometry. Let's get started with talking about surface area of pyramids and cones. So let's get into some definitions first. We'll start with pyramids and then we'll check out some stuff about cones as well. And so what is a pyramid? These are probably the most famous examples of pyramids, the pyramids that we see in Egypt. They happen to be square pyramids because the bases of those pyramids are squares. But we can have other types of pyramids as well. The base can be a different shape. A pyramid, though, is just this. So it is a polyhedron. So we have all these sides, all these faces being polygons, no curved parts to these, in which the base is a polygon and the lateral faces, so the parts around the shape in a sense, or around the polyhedron, the lateral faces, not the non-base parts, are all triangles. So these are triangles. Just like in the Egyptian pyramids here, you've got a triangle right here. This face right here would be a triangle, another one right there, and so on. So they're all triangles with a common vertex. The vertex just being the point up here at the top where all the triangles meet. And a regular pyramid, a little more specific, just like a regular polygon has all same sides, are all congruent sides, all congruent angles. A regular pyramid is like that, in that has a regular polygon for the base. So that could be, you could have an equilateral triangle as the base. That would be a tetrahedron. We learned about those already. And you could have a square, you could have a regular pentagon, regular hexagon, and so on. So it has a regular polygon for a base, and its height meets its, or the base, at its center. So in a sense, it's going straight up and down. The center of this pyramid, the square of there, would be right about there, and as you go up, it meets it right where its vertex is. The height and the center of the square, they have that in common. This is perpendicular, straight up and down right there. So let's also, I think I wanted to mention that, yep, right here, I'll put in one of the two big guys for this lesson. So the surface area of a regular pyramid. What's that formula? We've discussed this already if you watched the introduction lesson. I have trouble spelling pyramid. I always want to put the R before the Y, but pyramid, P-Y-R. Theorem 12.4 is this one right here. So this is one of the big things to know for this lesson. And I feel like you should know what these letters stand for already, so I'm just going to write down that S equals, well, let's think about it. We've got this pyramid here. Just in general, let's draw a picture off to the side here of a square pyramid. So for that, to start, we're going to erase some of these, so hopefully you're using pencil with this. If not, just wait till the end here. But I usually start by drawing something like that, a square, but it's on an angle. You're looking at it on an angle, so it looks like more of a parallelogram. And then from the center, I'm going to go straight up, and then I'm going to connect that to there. I'm going to connect that vertex to all these vertices of the square there. And this one I wouldn't be able to see, so I'll make that one dashed. And then from there, I wouldn't be able to see those ones, so I'm going to make these dashed as well. And in a different color, let's draw a couple things in here. We would have this would be my capital B, the area of the base right here. And as I move up from here, I would have the height, but we actually don't need to know that information to figure out the surface area of this. To find the surface area, we'd find the area of the base, and the area of all 4 triangles in this case. If it was a pentagon base, you'd have 5 triangles. If it was a hexagon base, you'd have 6. If it was a triangle base, you'd have 3, and so on. What we really need to find is the height of each one of these triangles and do 1/2 base times height for each triangle, but we can do the perimeter of the whole thing and find all the areas of the triangles all at once that way. And so let's do this in a different color. The slant height is what that's called. It's perpendicular to the base of that triangle right there, but this is called the slant height. We refer to this with a lowercase l. So this is, again, slant height. It's the height, but on a slant right there. So that right there, that lowercase l, I'm not sure why they use a lowercase l for slant height. That's just the letter that has been chosen and accepted by the math community. So this is a capital B for the area of the base. That's the square part in this case, plus 1/2. And again, this doesn't have to be a square pyramid. That's just the one that's most common, I would say. So 1/2 base times height for each triangle, but to do it all at once, do perimeter times slant height. And so this is the major thing, or one of the 2 major things to remember for this lesson. And this part right here, if you're ever asked to find the lateral area, that right there is the lateral area, the LA part. So let's check out an example at this point. So this is a square pyramid. Our next one, we'll check out here in example 1. We're going to draw a hexagonal pyramid. So make a base that is a hexagon. We're looking at it on a slight angle. It's going to be a regular hexagon, but I'm going to draw my vertex right there. I'm going to connect down here. Vertices would be, that one's a little off there. So just do the best you can with this. And then I'm going to have a vertex here and here, connect those with dashed lines. You could draw the hexagon first and then erase things later as well. That would work just fine. But here's a decent picture of we're going to say that this is a regular hexagon. And so I'm going to put in little marks here, 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 and here to denote that. So I have a regular hexagon base, and I'm going to tell you some values here. Let's do this in a different color. Right here, that the slant height equals 9 feet. And I'm going to tell you that the side length is 4 feet. So 4 feet from here to here. That's 4 feet right there. So what formula are we going to use if I'm asking you to find the surface area? Well, it's the one we just wrote down right here. S equals B plus 1/2 P times L. So we have the area of the base plus 1/2 of the perimeter times the slant height. So which of these values do we have? Which ones do we know? Well, we definitely know the slant height. It's given to me right there. It's 9. Do I know the perimeter? Not directly, but I can find it very easily. Just take 4 and multiply it by 6. That's the perimeter of the base. That's what the P stands for. The base part, though, that's going to be the trickier part. So right here, let's draw a picture down here of a regular hexagon. Just do the best you can with that. So a regular hexagon base is what we have here. And so I'm just recapturing that part of the pyramid down here. And what's something we know about regular hexagons, that little shortcut that we can use to find the area of a regular hexagon? We could use that apothem method, but I prefer not to. If I don't have to use it, use the trig to figure this out. And if I can use a shortcut, let's do that instead. And I can do that here. I can split this into 6. Do you remember 6? What kind of triangles are these? These are going to be, with hexagons, it's always going to be 6 equilateral triangles. And so we know that this would be congruent here and here as well. You'd have 4, 4, and 4 all the way around there. And so we can take this and find the area of the base by taking 6, because we have 6 of those triangles, and multiplying it by using that formula, s squared radical 3 over 4. So we're going to have that plus 1/2 times the perimeter is going to be 6 times 4. times the slant height is 9. And so right here, let's make a little note. Since the base is a regular hexagon, we can find the area of the base by using 6 equilateral triangles. And so that's that equilateral triangle formula, s squared radical 3 over 4, or the expression that yields that value. And so here I'm going to have 6 times my s is 4, so I've got 4 squared times radical 3 over 4, plus I can simplify this right there, that'll be 24, and still times 9. So let's continue the simplification here. This will be 16, so I have 6 times 16 rad 3 over 4 plus half of 24 would be 12, so I'll do 12 times 9. I'm just multiplying 1/2 times one of these numbers. This is not distribution. I see that mistake often, so be careful of that. It's not this plus this in parentheses. That's when we would distribute. From here, let's reduce. Let's use our different color to reduce this part right here. This would be a 4 and a 1. And so you've got 6 times 4 radical 3. That becomes 24 radical 3. And then over here, 12 times 9, that would be 108. This would be an exact answer. You can't combine the radical part with the non-radical part. And so if you were asked to give an exact answer, this would be it. You would say this in feet. This is area, surface area, feet cubed. If you were to approximate this with 1 decimal place in a calculator, I'm just going to go with 1 for now because that's what I said I was going to do. It just depends on the directions. Make sure you read those directions and do what it says to do in terms of rounding or not rounding, exact answer or approximate answer. So we'd have 149.6 feet squared. And so remember that you can do this with hexagons, but let's make a little note of this. So remember, equilateral triangle shortcut only works with hexagons. So you may have to go back, review that apothem method. So if it's a pentagon, heptagon, octagon, etc., we can figure out the area of a square easy enough and an equilateral triangle easy enough if those are the bases. But if it's like this instead, you have to use the apothem method from lesson 11.2 to find capital B, the area of the base. Okay, so make a note of that. That's important. Don't just assume that you can always split any base, any old base, up into equilateral triangles. That is not true. That only works with regular hexagons. And now let's check out some stuff about cones. So a cone, what is a cone? Some famous examples of cones here. If you're hungry, sorry, ice cream. I don't eat it much because I know it's not that good for me, but man, does it taste good. Oh my gosh. So a cone is a solid with a circular base. So it's not a polyhedron because it has some curved parts to it. It's got that circular base and a vertex that is not in the same plane as the base. So if I were to look at this right here without the ice cream in it, I'd have this circular part right here, and then this vertex right here, it's not in the same plane as that circle right there. So the points of the cone will all meet at that. Right here, the vertex is right there, the circle part is right there. It's got this extra part here so it doesn't topple over, but not in the same plane. The vertex ends up being up here. I could have a vertex over here. This would be an oblique cone, but I couldn't have it right on the circle because then you don't have a three-dimensional shape. It's just a two-dimensional circle instead. So as the base, and we've got right cone. So we had a regular pyramid, now we've got a right cone. Think of right triangles, think of that idea, think of straight up and down or perpendicular parts. That's what we have here with a right cone. So it's a cone where the height meets the base at its center. So here, both of these happen to be right cones because the height would be this part right here, and it meets the base right at the center. It is also perpendicular there. So right here, same thing. The height meets the base right at the center. It's a right cone. It's not oblique like this one on an angle. And so let's draw a picture down here to go along with the formula, just like we had done with the pyramid. The other big guy here, the other big kahuna, the surface area of a right cone can be found like this. This was the surface area of a regular pyramid. The surface area of a right cone. This is theorem 12.5. And that one, it's the same exact formula, but it's a little more difficult to put in the pi and the r. It's the same idea, I should say, at least, that you are taking, not the same exact formula, the same idea. We have a base, and we also have this lateral area part, but the lateral area part isn't found by using the triangle formulas because we're not going to have triangles as we go around this lateral part. So we're not going to get into the specifics of why the lateral area part works. The base, though, it should be clear that it's a circle, and the area of a circle is pi r squared. So that hopefully makes sense for the base part. But then this part, you're just going to have to kind of memorize for now, and again, we're not getting into why that is. That might be a video for a later time, an explanatory video as to where this comes from. But pi rl is the lateral area part. So we put this together. This is the base part. This is this part right here. And then the pi rl part would be the part as you go around here, the area of the lateral area portion of it. So right here, this is the base, and this is the lateral area. This, though, is the formula we need to know, we need to use when we're trying to find the surface area of a right cone. And so let's draw a little picture off to the side here of a cone. That's usually how I draw cones, is just I'll make a line coming down a little bit of an angle like that, make a half circle, and then complete the circle in the back with a dotted line or a dotted arc, dotted curved segment there. A curved segment, is that an oxymoron? I don't think that's a possibility. A segment is by nature straight. But anyways, we've got here my base is a circle, which is pi r squared, and you've got your r part, the radius would be right here. This would be your height, but we don't need to use that in the formula. However, we may need to use height and radius to figure out this part, this L part right here. Let's go over that. That right there is the slant height right there. So L is the slant height once again. So sometimes you have to use the Pythagorean theorem. That also applies to this. If you knew a height right here and half of the length of the base, you could use that to find the slant height for a pyramid as well. So we've got that. Am I missing anything? This would be the vertex right there. And the lateral area, yeah, I feel like we got it all. So we talked about the lateral area being the part around the non-base parts. And so let's check out, to finish example 2, I can put this up here. And let's draw a cone. This is not necessarily drawn to scale, you're just drawing any old cone. and we're going to say that this from here to there is 5 inches, so the radius is 5 inches, and I'm going to tell you in this case that this is 8 inches. Again, you might have to use a Pythagorean theorem sometimes, but we're not going to do that here in this one. So if you were given the height instead and the radius, you'd have to use leg squared plus leg squared equals hypotenuse squared to find the slant height. This one's going to be a little more straightforward though. So we've got the surface area is pi r squared plus pi RL, just using the formula that we just wrote down right there. Plug in the values that you know. We know the radius is 5, and we know the slant height is 8. So there's really nothing extra to figure out on this one. No preliminary work is necessary. Just plug the values in, and you'll have your answer. This would be 25 pi plus 40 pi, which we can put together, combine the pi's together. You've got 65 pi. Man, if you're hungry, this is a rough lesson for you. Talking about ice cream cones and pie, and man. This would be in inches, surface area, inches squared. I've got my units of inches over here. You approximate that in a calculator. Use that pi button on your calculator. Don't just type in 3.14, because the pi button will give you a much better approximation. Unless it specifically tells you to use 3.14, then use the pi button. So this is exact, and this is your approximate answer. And at this point, I'm going to stop it there. Again, don't forget though, you might have to use the Pythagorean theorem sometimes to figure out the slant height for both cones and pyramids. But we'll check out some problems together in class as well. Hope you do well with this lesson, and make sure you know these vocabulary terms as always. If you notice any of these that you're like, I have no idea what that is, hey, go back and review or check out your book, check out the definitions there in the book, and make sure you're familiar with those. And have a good day, everybody. I will see you in class if you're one of my students, or I will see you later in one of the videos.